We're surrounded by this incredible technology all day long. Our phones, our laptops, they're practically a part of us. But have you ever really stopped to wonder what's actually happening inside that little black box? Well, today we're going to pull back the curtain and take a look at the amazing, intricate dance of components that powers our entire digital world. Think about it. Every single day you're tapping, swiping, typing away. Just one touch can launch an app, connect you with someone on the other side of the planet, or start a movie. But that simple little action, it triggers a lightning-fast conversation between dozens of super specialized parts. So what is really going on under the hood? You can think of your computer kind of like a team of world-class experts. You've got the brain, you've got the memory, the eyes and ears, but none of them are any good if they can't talk to each other. The real genius in computer design isn't just about making one part faster. It's about making them all work together in perfect, seamless harmony. So how do all these different parts talk to each other at these, mind-boggling speeds? Well, they use a kind of internal information superhighway. Let's take a closer look at how that works. Okay, so this superhighway has an official name. It's called the system bus. And really, it's just a set of electrical pathways that acts like the computer's central nervous system. It's what connects the brain, the processor, to the memory, and to all the input and output devices like your screen and keyboard. It's the backbone of the whole operation. Now, what you've got to picture here isn't just a single road. Oh no. This is a multi-lane highway, and every single lane has a very specific job to do, making sure all that data flows smoothly without any traffic jams. The first lane, that's the address bus. It's basically the system's GPS. The processor sends out a memory address on this bus saying, hey, I need the data from this exact spot. The second lane is the data bus. These are the trucks, the heavy haulers, that actually carry the data to and from that address. And finally, you've got the control bus. This is a bit like the traffic lights, sending out signals to manage the whole process and make sure everything happens at precisely the right time. Now, how wide this highway is, specifically that address bus, has a massive impact. Did you ever wonder why older computers couldn't handle more than 4 gigabytes of RAM? Well, this is exactly why. A 32-bit bus can only handle about 4 billion unique addresses, which tops you out at 4 GB. A 64-bit bus, on the other hand, well, it can handle a truly staggering amount of memory. We're talking over 16 times billion gigabytes. Okay, so the internal communication is all sorted out. But what's the point if the computer can't talk to us? That's where input and output devices come into play. They're the translators, turning our physical actions into digital signals, and then turning those signals back into things we can actually see and hear. Let's just take the touch screen for a second. There are two main kinds. You've probably used a resistive screen, maybe at a restaurant or a self-checkout. They have these two flexible layers that you have to physically press together to register a touch. But your smartphone, that uses a capacitive screen. It has a layer with an electrical charge, and since our bodies are natural conductors, your finger disrupts that charge and the device instantly knows exactly where you touched. Pretty cool, right? And this is the kind of technology that gives us the incredible displays we have today. You'll hear manufacturers throw around all these fancy terms like OLED or Super Retina, but the number you should really pay attention to is pixel density, or PPI. The higher that PPI, the more pixels are crammed into every single inch, and the sharper the image is going to look. All right, that incredible screen needs data, and it needs it fast. Which brings us to our next big challenge. See, the computer's brain, the CPU, is an absolute speed demon, and it demands data instantly. The problem is, memory that's fast enough to keep up is extremely expensive, and we also need huge amounts of storage for all our files. So what's the solution? A very, very clever system of trade-offs. First up, right next to the CPU, you have the cache. Think of this as your desk. It's pretty small, but everything you're actively working on is right there, ready for immediate access. It's designed to hold the data the CPU is most likely to need next, and it is blindingly fast, absolutely critical for performance. The next level out is RAM, the computer's main memory. So if the cache is your desk, RAM is like the filing cabinet in your office. It holds way more stuff, but it takes a little bit longer to go and retrieve what you need. This is the active workspace for all your currently open apps, from your web browser to your photo editor. So what happens when that filing cabinet gets totally full? Well, the computer turns to virtual memory. Think of this as like an off-site archive. It uses your hard drive to pretend it has more RAM. It gives you a huge amount of extra space, but getting data from it is much, much slower. It's a crucial fallback for sure, but it's one you want to use as little as possible. And this, Right here is the memory hierarchy in a nutshell. It's this tiered system designed to create the illusion of a single memory that's both massive and incredibly fast. By cleverly managing where data is stored, the computer gets this perfect balance between high performance and reasonable cost. It's a brilliant solution. So, when this whole system works perfectly, you get what's called a cache hit. The CPU needs a piece of data and boom, it's right there in the cache. This is the ideal scenario. This is the system running at peak performance, giving you that snappy, responsive feel that we all expect from our devices. But if the data isn't in the cache, you get a cache miss. The CPU has to take a little detour and fetch the data from the slower RAM. Now, it's a minuscule delay to us, but in the world of computing, it's a significant performance hit. You know that tiny stutter in a high-end game or a dropped frame when you're editing video? That's often the real-world impact of a cache miss. The entire hierarchy is built to maximize those hits and minimize the misses. So, we've connected everything inside the box, and we've connected the box to us. The final piece of this puzzle is connecting our computer to the rest of the world, to our printers, cameras, hard drives, and of course, the internet. Back in 1996, the very first Universal Serial Bus, or USB standard, was introduced. Its maximum speed was 12 megabytes per second. At the time, that was revolutionary. Now, just keep that number in your head for a second. Today, the latest USB 4 standard can transfer data at up to 40,000 megabits per second. I mean, that is just a mind-blowing increase in speed, and it perfectly illustrates how our demand for data has absolutely exploded. But you know, raw speed is only half the story. The real reason USB became so dominant was its sheer simplicity. It introduced plug and play, so you suddenly no longer needed to be a computer expert just to install a printer. You could connect and disconnect things without restarting your home machine. It could power our gadgets. This user-friendliness is why it became the one standard to rule them all, simplifying everything for everyone. And that really brings us to the key takeaway here. From that internal system bus to the memory pyramid to the USB port on the side, the genius of modern computing isn't about any single amazing component. It's about the elegant and clever systems that balance all these competing demands, speed versus size versus cost, to deliver the seamless experience we all just take for granted. In the end, it really is all about solving communication problems, which, of course, leaves us with one final question. As we connect everything from our cars to our homes to our own bodies, what's the next great communication barrier our technology will need to overcome? What will the next information superhighway even look like?